All right, so here we go. So the assignment that most of you are currently working on is this command line assignment. And you're also, I encourage you also to, if you're done this, to just move forward and look as far forward as you can and dig into the later assignments. That would be great if you could do that. So everything that you need to do is described in these instructions. Now today, I'll continue with this list of topics. And each of these links here goes to a web page where I have some notes, just notes to myself, really, of things that I want to talk about in lecture. And you're welcome to look at the notes, but these notes come from this tutorial here. And this is part of your reading. And just to remind everyone once again that there's a lot of detail here. And I don't expect anyone in here to absorb all of the detail. But you should at least become familiar with the main concepts, important details. And a lot of the details you can just make a mental note of and know that you can go back and look at those things up when you need it. All right, so today I'll continue by talking about the next chapter in the tutorial, which is on variables and types. Before I do that, I didn't talk about the syllabus yet. There's really nothing for me to say. Juan Navarez's email is right in here. So someone asked me about that this morning. That's where you get that. And my office hours and the lab meeting times, all of that is listed there. And you might want to look through this. This is an area that you'll need to think about. This readability criteria. So when you write source code is meant to be read by humans and computers. And the computer doesn't care if it's sloppy or not organized. As long as it's syntactically correct, the compiler will translate your source code into a program. But when a human reads it, then it's a problem if it's not organized in a way that enables the reader of the code to understand the logic in your code. And so I have listed here some important principles of readability. And when Juan or me sometimes will look at your source code and score it for a grade, that we'll be applying these readability criteria to your code. So you might want to look through this. And I'll say the most important of all of these is this one right there, logical indentation. This is the one that you want to focus on first. Understand what this means. This is the most important. In code, you've got these statements. There's like commands. You're telling the computer to do something. And so that the program is really a sequence of these commands. And there's some branching and hopping and looping as well, so it's not a linear sequence. But when the program runs, and you make a record of what happens, it's one thing happens after another. So you can think of it as a sequence of commands. And the commands are sometimes a piece of your program. There's a command that has subcommands in it. So you have a statement with substatements. Well, the substatements should be indented to show visually to the reader of your code that those are substatements within a larger parent statement. And this is the most important code organization principle that I have discovered that students need to learn at this level. Okay, so make that your focus to understand how to indent your code properly to demonstrate this relationship between child statements and their parent statements that include the child statements within them. I'll give you an example. You see, these lines are indented within the function main. That's because they're sub-expressions within the larger expression which defines the function. And you can see that this opening brace here and this closing brace, that brackets the substatements within that larger statement. And we just emphasize that the compiler doesn't need that indentation, but the humans need it in order to see that relationship more clearly and easily. All right, so that's the syllabus. Any questions about anything? So let's talk about variables. A variable names a portion of memory that represents value. All right, so these are topics, these are things I need to talk about. So let's go ahead and just play around, experiment with some code, and then we can get a better feeling for what these ideas are about. So here we have a program in the folder basics, right? This is what your workspace should look like as you do these assignments. So here's a program. It's hard to read that, isn't it? Can I make that larger? Yes, I can. Look at that. Oh, is that nice? That's great. Okay. And then we need the terminal window down here, so I'll add that, a new terminal window. The ls to see the contents of my current folder. Oh, what is my current folder? Oh, it's this workspace inside my home directory, /home/Ubuntu. So my username is Ubuntu in Cloud9. Your name is Ubuntu in Cloud9. And workspace is the I think workspace is the just a folder. Yeah, it shows Ubuntu as a user here, so that's the user. So this is called the home directory here, home/Ubuntu. And we can get to it. We can cd to the home directory. We can use tilde as a symbol that represents the home directory. So that drops me into the home directory. This is a part of the first assignment to learn how to do this. We're working at the command line now. And so you'll need to practice this. Try to practice every time you sit down to do work. Just try to practice what you remember, and whatever you forgot, look at your notes, and then re-practice something until you get it committed to memory. All right, so then we have workspace. I'm going to go into the workspace and then basics. Here's the program ex1.cpp. That's this one right here. And I'll just print here. I'm just testing, make sure everything works right. So I want to compile the program. It's silent. Silence means it succeeded. ./a.out. So this generates a.out. The compiler here, C++, generates the file a.out. Now that star there, I think the star might mean that it's executable. I don't see that normally. Let me use the -L. option in the ls command to see if I can get any more information. I don't know what the star is there, because if I use command completion, I don't see a star. If I put a star in there, it runs it with a star. I've never seen that before. I don't get it. What if I put something else there, like a hash mark? No, nothing. Well, why don't I just type in a dot out? Why don't I just do that? It says command not found. Does anybody know why I type in a dot out directly? I can't execute the program. It says it can't find it. How can I find it? It's right here. Look at it. There's a dot out right there. I got to go /a dot out. What does that mean, /?
It's finding the hidden files.
Huh?
Isn't that finding the hidden files in there?
Not hidden files. Dot represents the current folder. And / is a separator character. It separates folder names and file names from folder names. So I'm saying command line interface, look inside the current folder and load and run a file, an executable file called a.out. So I'm giving the path to it, see? If I cd dot, that's similar to dot, right? Dot is the current folder, dot is the parent folder. I'm up to the parent, see? Now if I want to run, I can use ls basics to look inside the basics folder, and I see that a.out is in there, and I can run that. I can say in the basics folder, run a.out. You see that? I don't have /a.out because I need to tell the operating system, I need to tell the command line interpreter where to find this file that I'm specifying as an executable to load and run. So if I go basic /a.out, it says, oh, okay, I know where, you're telling me where to look. I'll look there and run that. But if we're inside basics, it won't look in the current folder. And I didn't tell it a folder to look in. But now if I go dot, I'll say, yeah, I'm in the current folder. Look in the current folder and run a.out. Now you can configure your system. Basically, when you enter in a command, like pwd or ls or where doesn't, or which. The ls is a command, the which is another command. And, I'm not sure that you studied that in the tutorial. Did they cover which? No. Anyway, you give an argument to which is some command you want. You want to know where this command is located in the file system, and it shows us ls is a program that's stored under bin. I don't know how I got off on that tangent there. So how does it, when I run ls, it finds it. I didn't say bin ls. I could, right? I can do bin ls to give it the path name to the file. That's called a path name. / start at the root in the file system, look in the bin folder, and then find a file named ls, and then load it and execute it. Load it and run it. But I don't have to give it the path name. But how come when I do a.out, apparently it doesn't find it? I have to give it the path name. But I don't have to give it the path name for ls. Does anyone know why? Because when you issue a command to the command line interpreter, it checks what's called an environmental variable, or the path variable. And a path variable is simply a list of folders in the file system that the command line interpreter should search to find that file that you're specifying. So I'll do an echo $path just to examine what the path variable looks like. That's the path variable. It's called an environmental variable. And so when I issue a command like ls, the command line interpreter starts by, it looks in here. That's a path right there. And see that colon? That colon is a path separator character. So that's the end of that's the first path I've highlighted. Then there's a colon which says, okay, that's the end of that path. Now the next path to search is this one. And then the next path to search is that one, and so on. You'll see that, look, in that path, there's /bin. See that? So the command line interpreter is going to search for, when I say ls, the command line interpreter is going to have, it will have searched all of these other paths first, not finding ls. And finally, it searches in /bin, and it finds a file named ls there, and it says, oh, that must be the one you want to run. I'll load it and run it. And that's how it works. This is how it works in Windows, in OS 10, and Linux, and probably any operating system that you could name. This is how it works. Just something to keep in mind. How many people need to change their path variable in Windows to get things to work right? Nobody does that? Well, in the old days, you had to go in and mess with that path all the time, but these days it's not as necessary, but it's there and it's running. If you go into Control Panel and search in your system settings and look at your environmental variables, you'll see this path variable. It's very important, actually, if you're working as a system administrator, especially, or just a programmer, you need to think about this path variable. And there's other environmental variables that you'll need to think about. I think ENV might list everything. Maybe there it is. These are all variables that are set in what's called the environment. But that's a little side quest we just went on there. I want to come back here. Let's come back to the C++ language. So I'm just talking about the command line environment now. Let's get away from the command line and then come back to the C++ language. Here is the source code. And we want to compile it. We enter in the C++ command. I wonder where that's located. Oh, it's under bin. It's the same as ls. So C++ ex1. I don't know why my command completion doesn't work here. CPP. There we go. And it generates a dot out. Now it says here. There we go. So we've got our little test code set up to do experiments with. So we want to understand what a variable is. Let's see what it says here. This is a list of keywords. When you create a variable in your program, it's it's like a math variable, like x equals 3, right? Or x plus y equals x plus 3. Y and x, those are called variables. It's similar in computer language. You have to think about it differently than a math variable, but they're similar. And they're similar enough so that people chose the same name variable to represent both of those ideas. So you create, just like in math. In math, you can invent variables. So I think I'll use epsilon to represent the weight of the object. So in math, you can create your own variable names. And when you're writing programs, you can create your own variable names. So you create these names of things that represent values, unknown values, or values that can change. Like the weight of an object put on a scale. Let's declare x to be the weight of an object put on a scale. So we'll do something like this. Double x. So I'm saying x is a double precision floating point value. So double is a short abbreviation for double precision floating point value. So in the computer, there's a distinction between floating point numbers and whole numbers, or integers rather. Now, an integer doesn't have a fractional part. So let's have another variable here. I'll call it int I. The I is a variable which is going to represent an integer value. We use the word int to declare I to be, a name of something which is an integer. Could be 3, could be -7, any integer. Any integer within the certain limits of what can be stored. So unlike in math, there's, you work in infinity all the time. You could any integer at all. But when you declare an integer like this in a program, there is an upper limit and a lower limit. So things in the computer are finite. Values in the computer, numbers are always finite. And here is another variable, x, which is a different kind of number. It's a floating point number, so it has a fractional component. So 1.5, we can say that x equals 1.5. And if we print x, let's print x. I'll do it like this. If we print x, and this says I'm going to print an end-line character. ENDL represents an end-line character. It's the same as printing an n, a \n, a new line character. Not exactly the same, because when you do this, you flush the output buffer in the output stream. See, when you write a new line character, you don't flush the output buffer. That's something you need to think about sometimes when you're coding, right? This flushes the output buffer. All right, but that's a detail that you can ignore right now. But later, if you become a C++ programmer, you need to remember that writing ENDL into an output stream flushes the output buffer. And what does that mean anyway? Well, I'm not going to get into that. So we want to print the x. So we should print, x is a value that represents 1.5. Let's run that. There it is, 1.5. And I is a name of an integer. Let's set that to 3. Oh, by the way, this is an operation here. This says assignment. It's different than a math equal sign. I mean, it represents something. It's just a different concept than you see an equal sign in the context of a math problem or a math idea. That represents it's used to specify equations, which are used to determine sets of n-tuples, things like that, right? So, but in a programming language, a single equal sign almost always represents an assignment operation. It means what's on the right side, you want to copy that and paste it into what's on the left side. So take the 3 and store it into the memory location in RAM that's named by I. So when you see I and X there, you should think, oh, those are memory locations. They're RAM. They're bytes in RAM. I is 4 bytes in RAM. X is 8 bytes in RAM. Usually. Doesn't have to be, but almost always. We need more bytes to store a value that has high precision with a decimal point. We need more bytes of memory to represent those values than we do to represent simpler integers. Now, if we want a bigger integer, we just make it a long. We say, I want a long integer. I want I to be a long integer. Now I is 8 bytes. So we've expanded the limit a bit. Now we can represent larger values. let's see in here. These are the data types. This is, long double. These are the fundamental data types. This is a long int. And these ints can be signed and unsigned. The default is to be signed. So here's an unsigned long int. That means the values that are represented are positive or 0. They can't be negative. They can't have a sign, a negative sign. That's what unsigned means. Unsigned means there's no negative sign. That it must be a positive value or 0. These are the data types. Here it is, double. These are the floating point types. Float is 4 bytes, so that's small. So if you're going to declare a floating point variable, usually you use double. If you're going to make a big block of memory to represent something like an image, then you might want to use a float because you'll use half the amount of memory. So if your application is using a lot of these things, then you need to be more careful about the precision that you decide to use to represent your values. If you can get away with a float, you're going to reduce the memory requirements by half. Then there's a long double. And it doesn't say, I was saying, that double is 8 bytes. I've never seen it not be 8 bytes. But according to the language definition, it could be anything. Anything that's not less than float. That's the only restriction. So the idea there is that you could actually have a different kind of machine, and that machine might have, its sort of native representation of numbers allow for larger or smaller values to be represented. And so the language allows for that type of flexibility. Here in this tutorial, they argue, oh, this is a great thing. But a lot of people think this is a weakness in the language, that I need to know how many bytes are in a double, because if it's not enough, I got to know that. So you want more control. So usually you want to exert more control and just say, well, any double that's good enough on this machine is good enough for me. That's usually not adequate for your problem. But anyway, the newer languages don't have this flexibility. Well, the scripting languages do, but like Java, C#, their data types that represent numbers require a certain number of bytes. So you have more sort of control over the size of data. All right, so let's carry on here. What else do I want to say? Oh, yeah, here, look. This is called a declaration. Here we're telling the computer, allocate 4 bytes of memory to be used as an integer, and let's call that area, that space in memory, I. So that's the name of that area in memory. And then this is an assignment. It says, all right, place the value 3 in those 4 bytes that are named by I. We can combine these two operations together into a single command. We can declare the existence of I, ask the compiler to generate code to allocate space for I, and then we can also initialize it to 3. And we can do the same thing for this double. And let's also, here on this line, we can actually cascade the output operation. So this is the same as cout x in one line and then cout endl in the next line. This is the same thing. And then we can have I. I'll put I first. Three and 1.5. Now let's get fancy. Let's say I want to put a string in here. I'm going to say I equals I. And then I'll do the same thing for x. I'll say x equals x. There it is. Now we can change these values. Let's change our mind about I. Let's set I to 4. So initialize it to 3, and then later, so these statements are being executed one after another in a linear fashion. We initialize the memory represented by I to 3, and then we write over top, and we write a 4 over top of it. Right, so we change I to 4. So I is now 4. What happens if we change I to 4.1? What's it going to print? Huh? Error? Maybe. Actually, I'm not sure. It might give me a warning, or else it'll just... See here, we're trying to put a floating point value and assign it to a variable that's of type int. So there's an automatic conversion that happens here. The 4.1 is manipulated into an integer. And it won't give a warning, I don't think. No warning. Just doesn't. All right, so now when I run it, what's it going to print?
Will print just 4.
4. See, 4.1 becomes 4. What happens if I did 4.99? Oh, a bunch of 9s there. What's that going to print? What would you print? You'd print a 5, right? Four. This thing is unreasonable. So it doesn't obviously think like a human. So what happens there is that when you assign a floating point value to an integer variable, you get truncation. So you lose the decimal component. It doesn't do rounding. It doesn't do rounding. Suppose we wanted to round. Suppose we want to round I. How do you do rounding? Rounding is very simple. All computer languages do this, by the way, all of them. Just add 0.5. So that's how you round it up, because it's going to truncate. That'll become, 5.4999, right? And then that'll be truncated to 5. Let me save that. There's the 5. So 4.1, same thing. What's that going to round to? 4.1 doesn't round up to 5, right? You want to round it up to, you want to round it down to 4. So are we doing the right thing? Yeah, we are, because when we add 0.5, we stay under 5. And that gets truncated, even though we're past a half point, there's no automatic rounding built in. We just get truncation. All right. Now, there's a new language. This stuff I'm presenting right now, you have to know. All right. Now I'll present something that you don't have to know. I won't spend a lot of time on this. This is a feature of the language that I have never used, ever. And let's create a new variable called j and assign that 9 to that. What's going to happen if I try to compile this thing? Anybody know?
Let's say J is undefined.
it's not, well, J is doesn't get, J is, yeah, J is undefined. I think that's what it's going to say. It hasn't been declared with a data type. Not declared. Very good. Good job on that. So what we could do is we could say it's an int. And now it'll, now it's defined. Or we can say that make J into, pick the reasonable data type for J. Do an auto assignment of a data type to J. Yeah, I think this is going to work. I think it's going to make J an integer. No, J is not an integer. How about if I do, oh, that's because I'm using the version of the compiler. What if I do V for version? Oops, C++. How am I doing this wrong? There we go. Well, you know what it is? How do I find out the standard? Do I... All right, so anyway, let's... This is not going to work. So I'm using a feature that's not a part of this, the version of the compiler sticking to. So let's set the standard to C++ 11. Now it works. Now the default standard is, the default version of the C++ language is not C++ 11. Now this tutorial here is assuming C++ 11. So in order to get that behavior, you need to tell the compiler to use that version like this. So anyway, this works. But how do we know, what J got set to? I'm sure it got set to 9. I don't have any problem with that. But what is its data type? Well, look at this. This here, I, the size of I is size of I. Here, I mean, use the size of operator here. Size of I. So it should be 4, right? This should print 4. Size of I should be 4. 4 bytes. The size is reported in bytes. Size of I is 4. So what's the size of J? What do you think the size of J is? Anybody want to guess? 4. That's what I think. Oops. Size of J is 4. So it probably made it an int. What happens if I did that? And I'm guessing, by the way, here. Okay, I think it's going to work. I want to make J into a long integer. And I think that changes. This is called a literal constant. It's not a variable. It's what it is. Right? It's a literal constant. And if you put an L on there, you're saying I want the longer form of it. I want this 9 to be thought of and treated as a long integer, not a normal integer. That's my hypothesis. Like I said, I don't use this. I've never used auto in any program. This is the first program I've ever written that uses auto. Well, maybe I had a baby program, you know, over the last quarter when I started looking at this. I used it maybe. So let's say, what's it going to say? I think J is going to turn out to be 8. That's my guess. There it is. Size of J is 8. All right. So the compiler is looking at this constant that's being assigned to J and deciding on the data type to assign to J. And I want to say that what I'm doing in lecture here is I'm playing around, right? I'm investigating. I've never done this experiment before. I read about this stuff, and I'm verifying that it's true by carrying out these experiments with you right now. But that's what you probably need to do this as well, as you, not for this example specifically, but as you read through the reading and work out the problems and start to learn this language, you're going to want to carry out these kind of experiments like I'm doing here. Yeah.
So size of any variable, we are just looking for the how many bytes is in there, or
Yeah.
Right?
Size of a variable is how many bytes are in the variable.
So if we are doing, if we add one more in J, so it's gonna be 12.
I mean, J equals J plus 1? What do you mean?
I mean, if we put 9L or any number, or later it's gonna be 12.
Any value?
Yeah.
Like that?
Yeah.
You think that's going to be 12?
No, just 3 digits.
3 digits? Is that good?
Yeah. So it's going to be.
No, that won't be 12.
It's gonna be 16.
No, it'll still be 8.
8.
Yeah. 8 bytes is a gigantic value. You can easily store 999 in 8 bytes. You only need 2 bytes for 999. So the L means I want it to be in 8 bytes, or I want it to be a long integer. Well, thank you for that question. Please ask questions as we're in the lecture. It's a good way to do it. Yeah?
I don't get what you meant. What does end L mean?
What does L mean?
End L?
Oh, end line. It's a new line character. It says, you know, let's suppose, watch this. Let's suppose we just printed hi. Okay? By the way, we don't need this recent version of the language at this point, okay? Actually, all the problems that you solve in the assignments, you don't need C++ 11 for any of those problems. So that would be considered an advanced topic. So I'll build this. Now what happens when I run that? Do you see the problem? You're supposed to say hi, right? Does it say hi? Yeah. It does. It says it right there. It says hi, and then it displays the prompt. Well, shouldn't it? It's not very nice. You want the prompt to be on the next line, right? So you don't want to just say hi. You want to say hi, and you want to output into the output stream hi, but you also want to output a new line character, which is an instruction to the console to go to the next line in its sort of visual, you know, display of the information. Now it's a new line character. You know what this is based on? In the old days, computers were first built, there was just like wires to get things to work. Then they used LED displays to, you know, enter in values. And then at a certain point, they had a device that was like a typewriter. And you don't even probably know what a typewriter is. You know what an old-fashioned typewriter? Have you ever been to a museum and seen a typewriter? I grew up in a museum, I think. So You know, in a typewriter, you type, and the thing has got like a spindle on it where the paper turns around, and the keys are banging on the paper, and it goes sideways every time you bang a letter onto the ink. It presses the ink under the paper. It's pressed against the spindle. And when you get to the end, you got to go. You have to move the spindle forward a little bit to the next line, and then you have to slide this thing over to start in column 1 again. That's called a carriage return, by the way. So N is a new line. That's turning the spindle. But it's not moving the type head back to where it should be. To move the type head, you need a carriage return, which is R. Is that right? Carriage return is an R. I think it's an R. But actually, it's not the right sequence. It should be carriage return line feed. So this thing is called a line feed. The normal sequence is carriage return line feed. So these are actually physical commands to this old, I think they call it a teletype, a terminal. So the /R is repositions the print head all the way back to column 1. And then /N is a new line. That turns the spindle 1 line forward, so the paper moves up. That's what these are based on. We still use them. Now, in Unix environments like Linux or Mac OS X, in character data, to end a line, you usually use just a new line character. But in Windows, they follow a different convention. They want a carriage return new line character. So there's conversion problems between character data created in Windows programs and character data handled in Unix-based programs. So it's something that you need to think about when you're working on stuff. And I got to tell you, this stuff comes up all over the place. This is stuff, this ancient stuff from the past is going to haunt us forever. You know, you look at the internet protocols, you know, for like doing web services and web pages, you see this stuff all over the place. You know, when you send a message to a web server, when your browser sends a message to a web server, it's sending character data in the form of lines, and the lines are use this sequence as a way of delimiting the lines. It indicates the end of a line. So you have a line of character data, and then you have a carriage return line. And it doesn't matter whether you're on Mac or Windows, but when you're using a generic general internet protocol, you've got to follow the protocol. So it's there. This stuff is present, and at some point you need to deal with this stuff. So things, let's see. Now reserved words that cannot be used for identifiers, we talked about that already. You know, you can't use, we talked about namespace last time, didn't we? You remember that namespace STD and auto. You can't create a variable called auto. You know, you can't do, you can't say that auto is an integer initialized to 3. That won't compile. We're using a reserved word as a variable name. So that will fail. So you cannot use these reserved words. This is the list of reserved words. You can't create a variable that's named else, and so on. Oh yeah, things are case sensitive. This is very important. So let's go ahead and create this, this integer I and set it to 3. And then we'll print I. All right, that should compile. That compiles. that runs. But, you know, what if we just said, well, I, that's an I, right? Is that going to work?
No.
The language is case sensitive. It says I is not declared in the scope. So if you want to use, you know, if you declare the variable with a lowercase value, then you have to, you know, use the lowercase version of it by, you know, so integer, you could, you know, you could, did I spell it right, integer? I think that's right. So this name is not reserved. Right? So variable names aren't necessarily one character in length. But if you declare it this way, you know, you have to use, you can't change the case. I can't do that. It won't match anymore. Whoops. Oh, what did I do? I do that all the time. So it compiled. No, I didn't save it. See that? I compiled it. But if I save it, it won't compile. All right. Now I talked about limits. So there's this header file called Numerical Limits. And let's take a look at this program here. Sorry. Yeah, this shows a little bit. Just to talk about your reading a bit. These are different ways of initializing variables. Here we're declaring A, initializing it to 5. Here we're declaring variable B, initializing it to 3. You know, we could have done, you know, equals 3, like that. But, you know, this is another way to express initialization to 3. Likewise, you can initialize C to 2 like this, right? These are all 3 different ways of specifying the initialization of an integer that you're declaring. And this is an uninitialized declaration of a variable, an integer variable. This is only valid in C++11. The default compiler won't support that. Let's see that. And I never used that. I've never used it. But they added it to the language for some very subtle reasons. I mean, it's there. But if we change the standard, it's all right. And the limits, numeric limits, if you're concerned about whether your variable as declared is big enough, you can always check with by accessing this header file numerical limits. And I have never used that before. I use a different approach, but let's take a look at this. So it's include, it's numeric limits. Numeric limits. The first time I ever did this. All right, so what is going on here? See the indentation? I want them to be this consistent. Not only am I indenting, but I want them consistent. I'm using tab. You know, the code I copied used 3 spaces. So I took the spaces out and I put in a tab because consistency is important. If you're going to use tabs, always use tabs for all your indentation. Don't mix tabs with spaces for creating indentation. Because tabs are represented with variable number of spaces. It depends on the editor. Some editors represent tabs as 8 spaces, others 4 spaces, and so on. All right, that's my lesson on tabs. So C out, and we have this numeric limits. Let's take a look at this. Do we have time for this? Yeah. Where is this thing? Here they're talking about the size of variables. Yeah, it's not there. Let me find it here. Numeric limits. This is going to be hard to read. And then it has something called a template parameter involved. The T is the template parameter. It represents a data type like int or string or a double. And these here are the members of this template. Must be a template class, numeric limits. So it's got some examples here. There they are. Oh, no, this is numeric limits is declared as a class, a template class, parameterized by a parameter t. Now this is advanced. You know, you have to learn. If you take 202, the next course, you'll need to learn this. You don't need to learn that for this quarter, but I'm going to present it very quickly right now anyway. So these are, you know, static member. This is a static member variable in this template class. So we use it like this. There we go. What's the largest integer in the system? So we want the numeric limits class to be parameterized by int. So we want the limits for numeric limits for an integer variable. And there's a static member variable in there. I think it's called max, or maybe it's a function. Is that a function? I don't think it's a function. I think it's just a variable. Let's take a look at that. That's not it. Maybe it's a function. That's not it. No such file. I got that wrong, didn't I? Numeric limits. What did I get wrong there? Did I spell it wrong? Looks okay to me. I don't get it. Should be all right. Numeric limits, no such file or directory? I don't get it. I'll have to study this and talk about it later. Oh, maybe I don't have the right header file for this. Oh, limits. It's called limits, not numeric limits. The header file is limits, but the class, template class, is numeric limits. There we go. Got it. All right, how big can an integer be? That's how big it can be. So if you need that number or any of these other values, like the minimum value and all kinds of things, then epsilon, this looks important. You know where to go for that. We talked about auto. I'm going to skip this decal type, but strings are important. So we only have a minute left here. Well, 15 minutes or 10 minutes. You go to 1:15 or 1:10? 1:15. Okay. I'll try to finish 1:10. All right. Let's talk about strings. This is important. Strings, this is required knowledge for this course. All right. Let's declare a string S and initialize it to high. So we say we want the variable S to represent the characters HI. Let's see if that works. We don't need that. So it's high. And then what about now string S is called an object. And these objects have properties that we can access using what's called the dot operator. For strings, it has a function or behavior called size. And if we do S dot size, it tells us how many characters are in S. Now, let's see. Let's see what it says here about strings. Introduction to strings. What's that?
Do we need to have a header file of the string?
You don't, except let's suppose we took this C out here, and we took these out. Now it'll complain that string is undefined. Let me show you that. So string was not declared in this scope. See that? We're using this data type string, but saying I don't know what string is. Because string is actually defined in a header file called string. So we'll need to include that header file. And now it's defined. Well, wait a minute, we never did this before and I just ran an experiment with it, right? That's because, see, these header files can include other header files, and they always do, almost always do. So when we include IOStream, if you dig into IOStream, you'll find that it includes other header files. And the header files that it includes other header files. Actually, ultimately, the string header file is included when we include the IOStream. And that's why this is sort of optional here. But I want to tell you that I have seen an environment, I think it was maybe in our labs. But you're working in Cloud 9, so you don't have to worry about that. But there are environments where somehow string does not get included. I can't remember now. To be safe, you would do it like this. It's not guaranteed that that string would ultimately be included, its definition included through IOStream. But in practice, that's the case. All right, now the strings, you can operate on strings. Like I can go S equals S plus Bob. So it should say hi, Bob. So we start with hi, and then we concatenate. That's a concatenation operation. If S was an integer, that would be addition. But because S is a string, the plus sign is interpreted by the compiler as concatenation. That means take the Bob string and paste it onto the end of the hi string. Let's see that. What else can we do? We can look at individual values. I can look at the first value in S. First character in S is H. The second character in S is I. Let's see, that's because we're going to get to this. This is an array index operation. So the string is a sequence of characters. And you can access individual characters using this syntax. And the first character is labeled 0. So counting starts at 0. It doesn't start at 1. First character in the string is S of 0. Second character is S of 1. What else do I want to say there? I think there's another type of string. They don't talk about it here. I don't want to overload people. I know everyone's overloaded already, so I don't see it here, so I'll skip it. What do you got? Constants here. So we'll need to learn more about strings later on, but not much more. So let's see what we've done here. Variables and types. Wow, I'm going so slow. Look at that. So I made lots of space in here so we can push back these topics. Maybe I'll go a little faster next time and skip some of the advanced stuff. But I wanted to show you that this article here, just to take a break here, how to hack an election. Did anyone read this? This was a crazy article. This guy here. I need someone to help me. That's Sepulveda, right? Sepulveda? It's not Sepulveda, it's Sepulveda. That's how I pronounce it? Yeah, okay. Andres Sepulveda. And he's been working in Latin America for almost a decade, it says here. And he's been basically rigging elections. I doubt he's the only one doing it. And he does it with his programming, right? And the article is just fascinating. He's been arrested. He's in jail, and the article goes into his personal history. It's very interesting. And he started programming and learned how to make websites. And he met this guy who he started doing work for, and he hacked into this political consultant's office. It's just to show him that he could do it. And the political consultant was just blew his top. He was angry at him, and then he hired him on the spot. He said, and then he was hired to do what? To hack into the computers of of the opponents, the political opponents that the consultant was working against. And it's a fascinating article. And one of the things that he does is he has a program that interacts with Twitter. He has created 30,000 fake Twitter accounts. And he uses them to engage people in conversation. Man, it looks like 30,000 people are all expressing some opinion about some guy, like Hillary Clinton is bad or Trump is bad, right? You may see that in your Twitter account or on Facebook or something like that. There may not be a person behind those messages that you're getting. So this guy in particular, and probably many others, are using code and information automation to fool people, to give them the impression that there's all this built-up consensus and interest in some particular, position or candidate or position that the candidate is behind, and they're fooling us. So this guy here has been, here's the back of his head. This is a web page syntax. These guys are fooling us. It's something to keep aware of. We're in an election year right now, right? You got lots of information you're getting from the internet, and you got to think about, where that's really coming from, and we're really being kind of manipulated by these people. I mean, that's something for you to think about. And I'll see you next time.